All right. Sound check, sound check. Do I hear myself? Yes, I do. And do we see? Well, we can't see it because it's covered by that thumbnail. Okay, now, do I see motion on the screen? Looks like we are good. Okay. Let's put away those headphones and let's get started. Sorry about yesterday. Just didn't feel that good. I mean, I wasn't particularly sick. It was more like, I don't even know. I wouldn't call it a headache. Just, I didn't feel like I would be able to sit through my usual 3-hour length if I had started at the time I was supposed to start yesterday. So I figured it would be better to postpone by a day, and here I am. And besides, most of you are probably just enjoying your winter break and aren't going to be watching this until a few weeks later when you're back into study mode. But for the few who have nothing better to do, I am here. Let's see. So, stuff to comment on. What do I want to start off with? Well, there was stuff from last time that needs correction. Oh, and before any of that, so if the screen looks different, I've played around a little bit with the settings. Last time I tried adjusting the focus to make it look better, and after reviewing the video footage, I realized that I made things a bit too blurry in my attempt to improve the focus. So I played around with it a little bit before this, and I think I have just the right focus level. This is as clear as it's going to get. I also played a little bit with the brightness and saturation, so hopefully that will help. I was hoping that upping the contrast would be good too, but because my lighting is not very even, that didn't work out. The results were kind of, well, let's not talk about it. So let me go ahead and show off the pages from last time now that I have them in better focus. Was this where we started last time? Yeah, so last time we started with this. So I'll leave that on screen for a couple seconds. And then we had this. And then we had this. Actually, I might be presenting these backwards. And then we had this. And then we had that. Okay, so hopefully for people who really wanted to see what I was doing and it wasn't clear enough from just hearing me say what I was writing, hopefully I didn't keep you waiting too long to actually see what was actually underneath all that blurry footage. I mean, it wasn't too blurry, but there were some parts, like subscripts of variables. Those definitely didn't look very readable in some cases based on what I remember from reviewing the footage. So that's the first order of business taken care of. Second order of business, there was a problem, I guess a bonus question that I did not properly answer. Yes, this right here. So I said I would look into this and come back with an answer later because it just wasn't coming to me. I know what I did wrong. I was looking for, and if you don't remember the context for this, just watch the previous stream. They should all be organized in a playlist. but we were looking for the range of masses that M2 can have for the system before the system can move. So we solved, let's see, we said the system would move one way if M2 was less than this, and we said the system would move the other way if M2 was less than this other quantity, and then when I tried to put the two conditions together, I got this mess. And the reason this doesn't make sense, the reason the greatest side is smaller than the smallest side, is because I simply forgot that I was looking for the negative of this inequality. These are the conditions under which the system moves, so if I want the conditions under which the system does not move, I would need to flip these inequalities before putting them together. So the correction is simply this. That is the correction, and now it makes perfect sense mathematically. I'm glad I actually bothered to check last time that the statement made mathematical sense. Otherwise, I probably wouldn't have caught that mistake. But yeah, there you go. In case you were wondering what was up with that, it has been solved. I forgot to flip the inequalities because I was supposed to take the logical negative of these two statements. This was an or inequality, and if you negate it, if you look for the conditions under which this is not true, then it becomes this and inequality. And if you don't know your or versus and inequalities, you might want to review your algebra pre-calculus stuff for that. The other thing I left you guys with was a question regarding air resistance. I asked you what would happen if... So we talked about an object that was simply... I think I assumed it was released from rest, even though the problem didn't specify at what speed it was released. I assumed it was released from rest, and I told you that the graph of its velocity versus time would look something like this under the influence of air resistance. When it starts with zero velocity, there's zero air resistance because the force of air resistance is given by that formula over there. Force of drag is equal to some constant times the speed. The v here is just the magnitude. It's not a vector per se. Well, actually, I guess it could be a vector. If I wanted to write this as a vector expression, I would say the drag vector, the drag force vector is equal to negative bv, and the negative sign indicates that it's directly opposite in direction to the overall velocity of the object. So yeah, I guess we could have used this version instead, but anyway. So if it starts from rest, if it starts with zero velocity, then there's zero drag force. So it would overall be speeding up, and I decided that down was the positive direction for this problem. So velocity would increase, that is, it becomes a greater downward velocity, and at first it just goes down at a rate of g, 9.8 per second. But of course, as it speeds up, some drag builds up, and the rate at which it speeds up decreases. At first it increases by this much over this duration. The next time that this duration occurs, we have only that much of an increase, which is a little bit less. The next time, the increase is only by that much in the magnitude of the velocity, and so on and so forth. So you can see the rate at which the velocity builds up gradually slows down until it levels off as it asymptotically approaches some sort of terminal velocity, some sort of terminal speed. And the question was, what if we reverse the situation? What if, instead of the object released from rest or some slow speed, what if we threw the object in such a way that its initial velocity was greater than v terminal? And I wanted you guys to figure out what would that graph look like if we adopt the same convention that down is our positive direction for this problem. So let's go ahead and talk about that. So basically, on your diagram, what it would look like is, well, when the speed has a magnitude of v terminal, which was mg over b, when the speed is mg over b, that is when the drag force is equal to the gravitational force, which would cause the net force on the object to be 0. So for speeds greater than v terminal, then the drag force, which increases as you increase v, would have to be greater than mg over b, which would make it greater than mg. Or wait, I worded that wrong. If v is greater than mg over b, then the force of drag is going to be greater than mg. That's what I meant. So you would actually start off with a larger drag force than a gravitational force. And we're assuming this object was thrown straight down, of course, so you would have a net force that's upward versus a velocity that's downward. So your acceleration, your net force is upward, so your acceleration needs to be upward, even though your starting velocity is downward. That means you start off slowing down. That means you start off, so here's v versus t. It would mean that you start off slowing down, and I'm just going to draw v terminal over here, for example. So that'll be v terminal. So you start off with some sort of high downward velocity. Again, we're using down as our positive direction. And you start off going down a lot. You're going down rather sharply because your drag is going to be pretty high, at least compared to your gravitational force. But as you slow down, the drag decreases. So at first, it's heading down kind of sharply, but then the rate at which it goes down itself goes down. And eventually it slows down until it's equal to v terminal. And once it's equal to v terminal, well, then the drag force is just equal to mg, and those two forces will cancel out, and there will no longer be any acceleration or deceleration. So it just slows down to terminal velocity. So in a way, you could say this is not only, the terminal velocity is not only a speed limit, but also a speed minimum. You could also think of it as a minimum speed that an object must have so long as it's falling in the presence of air resistance, until, of course, it hits the ground, and then all bets are off. But while it's in the air, it will have to have some sort of minimum speed eventually, after it's been moving for a long enough time. You can't force it to keep going slower than terminal velocity. I guess that argument made more sense in the first scenario, really. I don't know where I was going with that. But yeah, you can't slow it down past v terminal in the same way that you can't speed it up past v terminal so long as it's falling through the air. And as long as you drop it from high enough or throw it from high enough, either or, with enough time it reaches V terminal either way, whether from above or from below. And that takes care of the problem I left you off with last time. So now what shall we do? I know one problem that I definitely want to go over today. But I'm not sure when to introduce it just yet. Let's look around and see if there's anything else we want to do first. Is the backside of this used? Yes, it is. Okay, time to grab a new sheet. Oh, and I guess one more comment before that. This and this, if I were to put both of these graphs together, these don't need to be symmetrical at all, because I don't necessarily start from whatever my starting velocity is over here when I start faster than V terminal. It doesn't have to be exactly as far away from V terminal as it would be for, it doesn't have to be, whatever this V initial is minus V terminal, whatever this delta V is, it doesn't have to have the same magnitude as the delta V between V terminal and 0. Hopefully that makes sense, because if I'm just picking any random velocity greater than V terminal, then I can't guarantee that there's going to be perfect symmetry. Just in case somebody was taking away the wrong idea there, just wanted to point that out. These two graphs are not necessarily symmetric. Okay, now let's look for a problem to start us off and see what we can do. Yeah, we've already done something like that, so I don't need to do that one. I think we already did something similar to that, so I'll skip it. Actually, wait, did we? No, I don't think we did. Okay, how about this one? So it says a car is traveling at 50 kilometers per hour. Uh-oh, unit conversions. A car is traveling at 50 kilometers per hour. V initial equals 50 kilometers per hour. On a flat highway. If the coefficient of friction between road and tires on a rainy day is 0.1, what is the minimum distance in which the car will stop? This is assumed to be kinetic friction because the car is already moving relative to the road. We would assume that the road and car are not moving at the same rates. That's just common sense. Let's see. And then the second part is, what is the stopping distance when the surface is dry and the coefficient of friction is 0.6? So we've got two different coefficients of friction. I'm going to call them mu wet equals 0.1 and mu dry when the road is wet versus when the road is dry. Hopefully this will teach us an important lesson about driving in rain and snow. If you haven't heard of the term of hydroplaning, you might want to look it up. Hydroplaning. basically, I guess I'm about to explain it, aren't I? Okay, so you might remember our explanation of how friction works is that there are these little bumps, microscopic bumps in the surface that you're trying to move along. And of course, there are also some microscopic bumps on the bottom of the object that's being moved along the surface, but let's just focus on the surface itself for now. And when it rains, what happens is water molecules will fall into these cracks and they'll start filling up these gaps. So these little circles are going to represent water molecules. And the nice thing about water is that it tends to flow and fill up holes as long as it's not, seeping through cracks in the road and going underground. So if it doesn't do that, if it doesn't just kind of trickle underground, then what can happen is you end up essentially with a smoother surface. Essentially, they end up creating this shape that's closer to being perfectly flat. And when you have less of those bumps and ridges, you have less friction. And so the roads are slipperier. Slipperier. I think I said that right the first time. Slipperier. Is that even a word? More slippery. This is why I'm not the English tutor. Anyway, let's go ahead and figure out what our stopping distance needs to be. Well, if we're calculating stopping distance, then we know that V final has to be 0. And we are missing one more kinematic value. We can't solve for delta x or time or acceleration with just those two pieces of information. However, we can get acceleration from this information. At first, you might think there's no way we can do that. That doesn't look like enough information, but surprisingly enough, it is. If I were to draw a diagram of our car, I could have just drawn a block and been done with it, but there you go. There's a little car on the road. Then we end up with, let's see, normal force of gravity equals whatever the mass of the car is. We don't even know the mass of the car. I'm just going to call it big M times G for force of gravity on the car. And assuming no air resistance, the only horizontal force here would have to be the force of kinetic friction. Force, friction, kinetic. And this is actually enough for us to figure out the acceleration of this car. So we can do net force vertical has to be 0. We don't expect the car to accelerate up or down after all. Net force vertical has to be 0, which means forces up minus forces down, or down minus up. It doesn't really matter which direction you consider to be positive here. Either way, you get normal force equals mg. The vertical forces must cancel out. Since there's only 2 vertical forces here, they must equal each other and face opposite directions. Okay, so that normal force is equal to the mass of the car times g. And now for the force of kinetic friction. The force of kinetic friction is the only horizontal force, so that's going to be net force along the x direction equals the force of kinetic friction equals the mass of the car times the acceleration. I guess I should have written the MA first, following my usual pattern, but I wrote my force of kinetic friction too soon, so pardon that. And then force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So it's the coefficient times the normal force was mg is equal to ma. The mass of the car does not matter because if we divide both sides by the mass of the car, it just cancels out. Acceleration is equal to mu g. And so we have two different accelerations. We've got the acceleration under wet conditions is going to be mu wet times g, mu wet times g. And the acceleration under dry conditions is going to be mu dry times g. And let's see, so with our accelerations, we can use which formula to calculate stopping distance? I guess third equation of kinematics would be best here. So I would do v final squared equals, oh, actually, I'm missing something. The negative sign. Yeah, if I choose right to be my positive direction, then left is my negative direction, so this kinetic friction must be a negative. Okay, and that means there are negatives over there as well. Okay, so v final squared equals v initial squared plus 2 times the acceleration times delta x. That's going to be 0 squared equals v initial squared. We're going to have to actually find the value of v initial in meters per second. I'm just going to leave a gap here for it. Plus 2 times the acceleration was negative mu g times delta x. Okay, let's go ahead and convert 50 kilometers per hour to meters per second. So 50 kilometers for every 1 hour converts to, well, every 1 kilometer is equal to 1,000 meters, so that cancels my kilometers and leaves me with meters. And then multiply every 1 hour is equal to 3,600 seconds, or if you can't make that jump immediately, 1 hour is 60 minutes. Cancel the hours, and then 1 minute is 60 seconds. Cancel the minutes and you get seconds in the bottom. Or if you do 60 times 60, 1 hour is 3,600 seconds. I will start doing that eventually, but I'll give some grace for now. Okay, so 50,000 over 3,600 essentially is what I have. 50,000 divided by 3,600 is 13 point a bunch of 8s, eventually ending with a 9, so I'll just round it to 13.89 meters per second. So 13.89 is what we need to put in there. Okay, so subtract 13.89 squared, and you get negative 13.89 squared equals negative 2 mu g delta x. The negatives cancel out, divide by 2 mu g, and we get 13.89 squared over 2 mu g equals our delta x, and now we can just plug in our two different mu values and see what the answers are for parts A and B, all in one fell swoop. So 13.89 squared over 2 times 0.1 times 9.8 gives me a stopping distance of 98.43 in the case of wet road, 98.43. So delta x wet, delta x under wet conditions is 98.43 meters. And what about under dry conditions? I'll just copy over the same thing I typed, except I will change the 0.1 to a 0.6. The convenience of calculators. If you don't know how to do this on your calculator, that is an important skill to learn, using the copy feature of your calculator. Of course, some calculators can't do this, but if you have a calculator like this or better, some of you are taking AP Calculus. I know you have better calculators that can definitely do this. Your graphing calculators or whatever, they definitely have this feature. You just arrow back to one of your recent equations. Once it's highlighted, you press enter, it gets copied over, and then you go back into it and edit whatever needs to be edited, and there you go. So definitely make sure you learn how to get the most out of your calculator's features. It will save you a lot of trouble. You won't have to retype things all the time. Anyway, I'm getting 16.40579. I'm going to round that to 16.41. Delta x dry, 16.41 meters. Would you look at that? So, under 6 times the friction, it's actually exactly 1/6 of the distance, if I'm not mistaken, because we can actually see it in this formula right here. Stopping distance is inversely proportional to the coefficient of friction. You can see that immediately. But yeah, if I do 98.43 divided by 16.41, I get 5.998, which is close enough to 6. Yeah, there's a 1:6 ratio between the wet and dry friction coefficients, and there should be the inverse of that ratio between the wet and dry stopping distances. So yeah, big deal. Very, very big deal. This tells you why it's important when driving in rain and snow to keep a greater distance between you and the car in front of you. In case you suddenly need to stop, you're gonna need a lot of distance in order to avoid a collision. Otherwise, you're probably going to end up trying to swerve off in order to avoid a collision with the person in front of you, and then you'll just end up colliding with someone to the side of you, or hitting a roadblock, or what do you call them? The concrete walls that are on the sides of freeways. Why am I blanking on what they're called right now? Guardrails? No, those are the metal ones. Let me think. Not guardrails. I don't know. I'm blanking on it. It's not that important. I'm sure it'll hit me after I end the stream, because that's how it always works with these kinds of things. Anyway, let's look for another problem. I mean, that one is... I think we've done enough of these problems where you start with kinematics. I want something a little bit different. What about this one? Let's see. We've got two objects on an incline. No, we don't need it. Okay, I think it is time to do the problem that I've been thinking about all week. Well, I haven't been thinking about it. I've solved it many times, but the problem I've been planning to cover this whole past week. So it says, what color do I want to use here? Let's use this one. This one I don't think shows really well, despite all of the camera settings that I've played around with. It still shows darker than it actually is. It's supposed to be this sort of brownish, reddish color. But we have the following situation. So we've got one block on top of another block. And the second block is a lot longer. So the first block has mass little m, the second block has mass big M. Little m is equal to 2 kilograms. Big M is equal to 8 kilograms. And it says, block of mass 2 kilograms rests on the left edge of a block of length L equals 3 meters. But according to the diagram, L is in fact not the length of the bigger block. It is just the difference in length between the two blocks. According to the diagram that they drew, L is just this over here. This is L equals 3 meters of distance. Okay, and these two blocks are on a, let's see, they rest on the left edge, or no. Block of mass little m equals 2 kilograms rests on the left edge of a block of length L equals 3 meters and mass big M equals 8 kilograms. The coefficient of kinetic friction between the two blocks is equal to 0.3. So mu kinetic, and this is just between the blocks, is equal to 0.3. And the surface on which the 8 kilogram block rests is frictionless. So these two blocks together, the bottom block is on top of a frictionless surface. A constant horizontal force of magnitude F equals 10 newtons is applied to the 2 kilogram block. So let's draw that. Here's a force. They just called it F. I'm going to call it F applied. Equals, what did they say? 10 newtons. Equals 10 newtons. So a constant horizontal force of magnitude 10 newtons is applied to the 2 kilogram block, setting it in motion as shown in the second part of the figure. So second part of the figure, they've basically drawn a before and after. Where did I put? There it is, that other pen. So they've drawn a before and after photo. That looks like this. So that's what they've drawn. And they are asking us the following two questions. Part A, How long will it take before this block makes it to the right side of the 8 kilogram block, as shown in their second diagram? They also note that both blocks are set in motion when the force is applied, when that green force over there is applied. So that's part A. How long will it take? So A, what is T? And then part B, how far does the 8 kilogram block move in the process? Part B, how far does the bigger block, the bottom block, move in this process? So that is delta x, I guess I'll call it delta x of big M. Those are the two questions. This is one of those problems that will hit students like a truck if their teacher has been doing nothing but give them plug into the formula and don't think types of questions, which is not really the essence of physics. This is one of those problems that a lot of students will get stuck on. But we can most definitely figure it out. The first step is to draw a good diagram. And I'm not just talking about a force diagram here. We also need to figure out how to interpret this whole diagram. So both blocks have moved. You can actually do this experiment yourself. Just take something, put two things on a table, and push the top thing. And if there's sufficient friction between the two things, so I guess if I take these two calculators, here's calculator 1, and here's calculator 2, has these nice little friction pads, although I guess 2 of them are starting to look kind of worn out. Wow, I didn't know that could happen. Huh. And if I push the top one, okay, that didn't work. Maybe if I try this surface, it'll stick a little bit better. Nope. Man. And here I was hoping, I don't know what I was hoping for. What can I use as an example? I need something where there's a good amount of friction between the two things. Otherwise, the top object is just gonna slide past the bottom one. Yeah, can't find anything. You'll just have to find something at home. I'm sure if you play around enough, you'll find something. You'll find something at home. Don't do anything dangerous, obviously. Don't go blaming me if you end up breaking something and your parents get mad at you. Not my fault. Not my fault. I plead the 5th. No, wait, is it? Well, yeah, I guess I can plead the 5th, but I also plead not guilty. My hands are clean. But yeah, you're going to want something that has good traction on top of something else that slides easily against whatever surface you put the two objects on, and play around with it, and you should be able to replicate this experiment. I lost my train of thought. What was I going to talk about next? So, top object is being pushed, and the second object is being dragged along with it, and that's because of friction. That is because of friction. So both of these objects move. So this object, this big M object, is going to move by this much. That's what I called delta x big M. Delta x big M. Okay, and what about this block? What about the small block? Well, the small block will have traveled, let's see, how do I want to define this? Do I want to define it from its left end to its left end or from its right end to its right end? I think I want to do it from its left end to its left end. So its left end has moved, let's use dark blue over here. Its left end, I mean, it doesn't matter in the grand scheme of things, but that's going to be delta x of little m. And we've got, I guess, this over here was the width of m. So this L equals 3 meters is the width of the little, no, hold on. How do I want to say this? So I'm trying to justify, here's what I'm trying to justify. I'm trying to justify that this right here is the same L equals 3 meters that we had up here. It's the same amount of length. Because let's say, for example, that this small block was, I don't know, 1 meter wide, and you push it to the exact opposite end over here. If this thing was 1 meter wide, or let's just call it, well, x is already taken. Let's say that this is w meters wide, so that the total width of big M is L plus W, is 3 plus W. Well, then it would follow then that if you subtract W from the right end of the big M block, then that would just leave 3 on the left end. I'm pretty sure that's really easy and really easy and intuitive for most of you, but sometimes even the best of us will have a little bit of a brain malfunction over something like this, so I think it's worth it to slow down and explain that. And also, the other thing is, it's worth it to slow down so that we don't take things like this for granted, so that we make sure the thing that seems really obvious to us is actually the truth, because sometimes things will feel obvious when they're not actually true. That's something you have to be careful about a lot in physics, in case you haven't noticed. If you haven't had a moment where something that felt obvious turned out to be wrong in physics, then there is no way you're getting to the end of the course without experiencing that at some point. I'd be surprised if you haven't experienced that already, but I would be absolutely flabbergasted if that persisted until the end of the course. There are a lot of counterintuitive results in physics, and it's only a matter of time. It's when, not if, you will encounter them. Rambling aside, I think we have everything we need to start setting up some of our math. So clearly, some kinematics are involved here. So we have the following relationship. We've got delta x of little m. Delta x of little m is equal to delta x of big M plus L, which is equal to 3. So delta x of big M plus 3. Okay, that's going to be useful later. Clearly, their initial velocities must have both been 0. V little m initial must have been 0, and V of big M initial must have also been 0. But since they didn't move equal distances, if they did move equal distances, then the small block would still be on the left end of the large block, so we know they didn't move equal distances, and since they have the same starting velocity, that must mean that their accelerations have to be different. assuming their accelerations were constant, of course. Actually, even if their accelerations were not constant, they would have had to have experienced different accelerations. So we know that a of little m is not the same as a of big M. So we know about the initial velocity, we have a relationship between their displacements, and that's really all we know. Oh, and one more thing. The amount of time that each one is traveling should also be the same. The amount of time that little m is moving equals the amount of time that big M is moving. I'm just going to call it a generic T with no subscript. So here we're just using one stopwatch to track the motion, because the motion of both blocks begins and I guess pauses from the same starting moment to the same pause moment. I say pause because there's no reason to assume that this thing just stops here. Okay, so I think it's time to find, since we only know one thing and we've got relationships for two kinematic variables between the two objects, it's time to try and figure out what the differences are between their accelerations. It's time to figure out what's going on with their accelerations, and for that we need force diagrams. So I'm going to draw two diagrams for my two objects. For my first object, I've got little m over here is going to have a mass of little mg, so that's going to be 2 kilograms times g. I'll just keep it as little mg for now. There's going to be a normal force on it due to the block underneath it, so I'm just going to call that normal force blocks. That's the normal force between the blocks. And of course we've got the applied force of 10 newtons, force applied. But there's also friction between the blocks, and the friction has to be opposite to the direction of relative motion. Little m moves to the right relative to big M. So the force of kinetic friction on it must be to the left. The relativity part is going to matter more when we draw the diagram for the second block. I think that's everything for the small block, though. Am I missing anything? No springs, no ropes. And if we have kinetic friction, then we can't have static friction on the same block. That just wouldn't make sense. Well, actually it can make sense if there was a third object that doesn't slide relative to it. But that's a more complicated problem, which I don't think I have in this book, but I could make one up. I could try and make one up. Maybe I should definitely do that at some point. I should just sit down and look through my book problems and see what kind of problem is missing. What kind of problem could I add to this? And maybe I'll just sell it as a worksheet. I mean, if people are willing to pay for it. The ironic thing is, if I did sell it, it would probably end up helping more people than if I did it for free. There's this weird psychology thing that goes on with people where if you give them something for free, they are actually less interested in it because I guess there's some sort of subconscious feeling of, if you're doing it for free, can it truly be that good? And to be fair, sometimes there are things that are too good to be true. I just saw some videos about a certain YouTube sponsor that's in hot water right now because someone did some digging and found out that they're kind of scummy. But now I'm rambling too much. Let's get back to the problem. So I guess I can... Do I want to write equations right now or just draw the next diagram? I'll draw the next diagram and then we'll do equations. So next diagram for the big M block. So this one is going to experience a normal force downward from the block above it. That's the normal force between the blocks. Those should be equal and opposite reactions. And then there is no force applied to it directly, so we don't have any applied forces. Of course, it's going to have its weight, mg. There's a normal force acting upward on it from the surface beneath it. I'll call that normal force table. Normal force table. I'm assuming this thing is on a table. You can call it whatever you want. Normal force surface. They never specified that it had to be a table, did they? No, they just called it a surface, but the drawing, it looks like some sort of glass table or something. Or a countertop. And then, well, we know something has to be moving this thing to the right. It moved to the right, and it was initially at 0 velocity, so it had to accelerate to the right. It has to have a net force to the right, and that's going to be the reaction to this kinetic friction force. That's going to be the reaction to that kinetic friction force over there. So I'm going to draw it over here. Force, friction, kinetic. No new label because they're literally the same force, at least in magnitude. They are action and reaction. So if the action and reaction logic doesn't make sense to you as to why this kinetic friction force is pointing to the right, think about the way that the bottom block moves relative to the top one. From the bottom block's perspective, it's as if it was moving to the left relative to the block on top. This scenario over here is equivalent to the bottom block moving left while the top block stays still. Top block staying still while the bottom block moves left from underneath it. So relative to the smaller block, the bigger block is moving left, therefore the kinetic friction force on it must be to the right. So two different ways to determine the direction of the kinetic friction. Actually, three different ways, if you think about it. You've got Newton's third law, and you've got the direction of the bigger block relative to the smaller block against which it experiences the friction. And third, the fact that something has to be pushing it to the right. Those are all dead giveaways as to the direction of this kinetic friction force. Okay, now we can write some equations. So let's see what I have. I haven't touched this color today yet. So we have for the smaller block, net force vertical has to be 0 because it doesn't accelerate up or down. So net force, I guess I'm going to call it little m y, is equal to, it has to be 0, has to equal normal force blocks minus the force of gravity, little mg. And that just tells us the normal force between the blocks is equal to little mg. Nothing surprising there. We've seen that numerous times before. What about the net force on the little block in the x direction? Well, that's going to be the mass of the little block times the acceleration of the little block in the x direction. I'm not going to add the x here because the only accelerations we have in this problem are going to be horizontal anyway. No need to go out of my way to specify that. And that's going to equal, let's see, force applied, which is 10, minus force of kinetic friction, which is going to be the coefficient of kinetic friction times the normal force between the blocks. And I forgot the k there. So that's going to be 10 minus 0.3 times mg, and we'll deal with that in a minute. Okay, next we've got for the big block, well, I actually don't need to do the vertical at all. If there was a coefficient of friction between the bottom block and the surface, then I would need to actually calculate the normal force between the surface and the bottom block in order to calculate that friction, but there is no second friction, so we are good. That is a bonus question you can ask yourself, though. Actually, here's an interesting bonus question. What coefficient of friction does the bottom block need to have with the table in order for the bottom block to not move at all? We know it's possible because we just saw it happen with my calculators. I tried pushing the top one, the bottom one didn't move at all. So we know once the coefficient of friction between the bottom object and the surface is high enough, you can get that sort of thing. So that's your bonus question to ask yourself. Can you calculate the coefficient of static friction, the minimum coefficient of static friction necessary to prevent the motion of the bottom block? And for that, you would do net force of big M in the y direction equals 0, and you would have to calculate the normal force between the table and the bottom block, so you could then use that to calculate the friction between table and block. So normal force table, and then minus, we've got two forces down, so minus normal force between the blocks, which we already know is little mg, and also minus big mg. Unsurprisingly, the normal force that the table exerts on the big block is just the sum of the weights of both blocks combined. And then net force on the big block in the x direction, this is the more useful one for the current problem, is equal to mass times acceleration of big M equals, all we have is force of friction to the right minus nothing to the left, so positive mu k times the normal force between the blocks. Okay, and that will allow us to solve for the accelerations of the two objects. So let's see, 0.3 times mg, so 0.3 times little m is 2, so that's going to be 0.6 times 9.8, what is that, 5.88? 0.6 times 9.8, yep, 5.88. So this over here is 5.88, and then 10 minus 5.88 is going to be 4.12, and so 2 kilograms times the acceleration of little m equals 4.12, divide by 2, and that's going to be 2.06. Acceleration of the smaller object is 2.06 meters per second squared. Okay, for the larger object, we just have the 5.88, so we've got 8 kilograms times the acceleration of the big block equals 5.88. Divide by 8. 5.88 divided by 8 is 0.735. 0.735 meters per second squared. Okay, this is an opportunity to check for mistakes. Does it make sense that the acceleration of the bigger block is smaller than the acceleration of the small block? Well, common sense would suggest if they both started from rest, the one that moved farther in the same amount of time must have had a higher acceleration in that direction. So, yes, this checks out. Always be checking for things like this. Do my numbers make sense? Are the numbers I'm getting making sense? Sometimes the answer to that isn't so obvious. As I said earlier, there are a lot of unintuitive results that occur in physics. But this is still a habit that you want to have. You still want to ask yourself frequently while doing various steps of a problem. You want to be asking yourself, are the numbers I'm getting making sense so far? And if not, double check your work, and either you've found something wrong or you've found something that you didn't understand as well as you thought you did. Either way, it's worth it to double check if you see something that doesn't look right with your numbers. But you won't spot that if you don't develop the habit of actually questioning your numbers. So always be asking yourself, does this make sense? Now that we have these two accelerations, though, we can finally solve the kinematics portion of this problem. So I guess we're going to flip over to the backside of this sheet. And what information do I need to copy over? We need to solve for t, so that's one thing. And then we know that the v initial is 0, and delta x of the small block is 3 more than the large, and 2.06 and 0.735. Okay, so v initial for both blocks is 0. Delta x of the small block is delta x of the large plus 3, and acceleration of the small is 2.06 meters per second squared, while acceleration of the large is 0.735 meters per second squared, both in the positive or rightward direction. Did I forget anything else? The time is shared between them, and I think we're ready to go. So I'm going to go ahead and start with this over here. I'm going to rewrite this, but with my delta x's substituted using my second equation of kinematics. Second equation of kinematics says delta x is equal to v initial times t plus 1/2 the acceleration times t squared. The good news is that v initial is 0 for both cases, so delta x of the small block is going to be 0 plus 1/2 acceleration of the small block times t squared equals delta x of the large block is also 0 plus 1/2, and then acceleration of the large block times t squared, and then that plus 3. And I know these accelerations. The only unknown here is time. And I don't have a quadratic, so this is actually going to be pretty easy. Just isolate the time and take a square root, and you're done. So actually, I can cancel out the 1/2 right away by just multiplying everything by 2. So yeah, let's do that. And that would give me acceleration small 2.06 t squared equals acceleration large is 0.735 t squared plus 6, right? Multiplied everything by 2, so the 3 becomes a 6 and the 1/2s are gone. Okay, and subtract 0.735 from 2.06. So 2.06 minus 0.735 is 1.325, so 1.325 t squared equals 6. Divide by 1.325, so 6 over 1.325 is about 4.5283. That's going to be t squared, and if I take the square root of that result, I get about 2.12798. I'm going to round that to 2.128. So I get t equals 2.128 seconds. I took a square root, but I know that I only need the positive root here. The negative root wouldn't make sense. Negative time does not make sense in our context. So 2.128 seconds, that's the answer to part A. Part B was just asking for delta x of the small block, if I remember correctly. Oh, no, delta x of the large block. Okay, I mean, we can solve for both. It's not really that hard. But yeah, delta x of the large block is just going to be 1/2 acceleration of the large block times t squared. So delta x large block equals 1/2 acceleration of the large block is 0.735 times this squared. What was it before I took its square root? 4.5283. 4.5283, give or take. And if I put all that together, I get 1/2 times 0.735 times 4.5283 is 1.664. I'm going to round it to 1.66 meters. And of course, if they asked about the small block, you would just add 3 to that and you would be done. So there we go. That's a problem that once you do it enough times and you think about it and reflect on it, it's actually not too bad. Once you have enough practice with this sort of stuff, once you practice the reasoning process, it's actually not too terrible. It's just the first time you see this, especially if you've mainly been doing problems that are very standard and just plug the numbers into the formula, so to speak. This will hit students hard if they see it after a long string of plug and chug problems. But it's actually not bad once you understand how to lay it out. If you would like to do a similar one, I won't solve this, but I do have a similar one in my other book. Let me find it. Where did you go? Not that chapter. Okay, I think I'm on the right chapter. Okay, here it is. I'll draw it and leave it up to you. I'm not solving this one. This is just for your own practice. It says there's a 42 kilogram slab. that rests on a frictionless floor. So this thing is 42 kilograms. The coefficient of static friction between the block and the slab, or no, wait, I misread. A 9.7 kilogram block rests on top of the slab. So there's a 9.7 kilogram block, 9.7 kilogram. That's not even readable, but you know what it means. 9.7 kilograms rests on top of the slab. The coefficient of static friction between the block and the slab is 0.53. So mu static, and this is of course the maximum, is 0.53. While the coefficient of kinetic friction is 0.38. Mu kinetic is 0.38. The 9.7 kilogram block is acted on by a horizontal force of 110 newtons. So there's a force applied of 110 newtons. And the questions are, what are the accelerations of the block and slab? So the questions are, part A, what is acceleration of the smaller block? And part B, what is the acceleration of the larger block? And if you want to call these S and L, S for small, L for large, I guess that works too. Especially if your lowercase and uppercase m's look the same. I would probably recommend going with that over what I did. Because you have to keep in mind, on the AP exam, the grader who is reading your work needs to understand your work. And if you create situations where some of your work could easily be, confused for other things, then that's something you need to take into account when naming your variables. But yeah, slightly different in terms of what they're asking for, but you can add to it if you want. You can add some number here to be like the distance between one end of the slab and the other end, and ask yourself a question similar to the one we just did. Note that one important difference is that they give you the coefficient of static friction, which introduces the possibility that the two objects might not move relative to each other at all, even though they will still move relative to the ground. Either way, they're moving relative to the ground, but will they move relative to each other? You're going to have to calculate and see if the static friction is enough to overcome the applied force trying to push this 9.7 kilogram block. And considering how high this applied force is, I'm going to go out on a limb here and say the answer is going to be no, but still do the math and check. And actually, a bonus question you could ask yourself then is, what is the applied force at, like the breaking point? Above or under which applied force will the nature of the motion change? So yeah, don't stick to, I know I've been repeating this for, let's see, I mentioned it a number of times last week, I believe, and I think 2 weeks before that or whenever, but don't limit yourself to just what the question is in the book. Ask yourself bonus questions. Ask yourself additional stuff that is actually solvable and see what you can do with it. See if you can discover something. See if you can discover like a pattern, a shortcut, a new formula. Not necessarily so that you can use it on the exam, but just to go through that sort of discovery process and broaden your horizons. Okay, so I'll put that away and let's go back to the more algebra-based book and see what other questions we can ask. Oh boy, here we go. The mother of all pulley problems. Okay, it's actually not that bad. So this one says, in the figure, which I will draw for you in a minute, the coefficient of, actually let me draw the figure first. It'll make more sense if I draw the figure first. Oh, and also for this problem, one more thing to mention. As you can see, it has everything going to the left. I would advise defining left as the positive direction for your horizontal here. I don't know why they didn't just go with, convention and just draw the same thing mirrored, but it's not something that you can't deal with. Okay, so back to this problem. So they have a double pulley. They have a double pulley here, and they have a block here, and a block on top of it, and a block over here. Well, actually, they drew this one as a ball, but I'm still going to treat it as a block. And we're going to have rope going over the pulley like that. And like that. Okay. So there is our situation. And the diagram also gives us that this is 2 kilograms, this is 3 kilograms, and this is 10 kilograms. And it says, in the figure, the coefficient of kinetic friction between the two blocks shown is 0.3. The coefficient of kinetic friction between the two blocks shown is 0.3. So I guess I haven't been doing this for the other problems, but wait, how many problems did we do? I guess 2. Yeah, I forgot to do this for the other problems, but I'll draw the tick marks to indicate that there's friction there. So there's a coefficient of friction of 0.3 between the blocks. The surface of the table and the pulleys are frictionless, so no friction with the table. Only between the blocks. They decided to go easy on us, but as I just finished saying, you can challenge yourself and ask yourself the bonus question, what if I give a mu k table? What if I have another coefficient of friction between the table and the bottom block? Anyway, mu k between the blocks is 0.3. And it says, draw a free body diagram for each block, determine the acceleration of each block, and find the tension in the strings. Determine the acceleration of each block. You would think, because of the way it's worded, that each block would have a different acceleration, which is technically true in the sense that each one will accelerate in a different direction, but the magnitude, common sense would suggest, is the same for all 3, unless those ropes begin snapping, but we wouldn't have enough information to confirm one way or the other whether those ropes did snap, so we're just going to assume they won't. And yeah, find the tension in the strings. So I guess we'll call that rope 1, and we'll call that rope 2, and I will call this block 1, and block 2, and block 3. And I guess I'll circle the numbers for the blocks. Actually, not too terrible. we've got 3 objects, so draw 3 diagrams. Diagram of block 1. We have a 2 kilogram block, and we're going to have force of gravity downward equals 2g, or I guess force of gravity 1. And it's going to have force of tension 1, pulling it to the left, force of tension 1. And it's going to have normal force from the block underneath it. I'm going to call that normal force blocks. It's the normal force between a pair of blocks after all. And let's see. If the system moves, I guess I should make an assumption about the direction of the system. So I'm assuming that this system is going to move like so. So I guess that's my positive direction. Counterclockwise for the first pulley and clockwise for the second will be my indicator of positive direction. So if the system moves at all, I expect it to move to the left. I expect the 2 kilogram block rather to move to the left, while the 3 moves right and the 10 moves down. So kinetic friction would be opposite to the direction of motion. Opposite of left would have to be right. So force of kinetic friction, if the system moves the direction that I assume it will move, it would have to be that way. Force of friction kinetic. I guess I should be more specific and call this force of kinetic friction blocks. Not important here, but for those of you who want to ask yourself that bonus question of what would happen if there was friction between the 3 kilogram block and the table, labeling your friction according to what 2 objects it's between helps you match the correct friction to the correct normal force. Right? If you're calculating friction between block and table, that would be based on the normal force between the block and table. If you're calculating friction between block and block, that depends on the normal force between block and block. Just a little reminder. I'm sure many of you have gotten tired of them, but I don't mind sounding like a broken record. I need my lessons to stick. Otherwise, why are we even here wasting our time? You're not sitting through this for 3 hours a week just to forget everything. Or maybe you are. Maybe you're just here to feel like you're learning without actually learning. That would be terrible. Don't let that be you. Is there anything else for the 2 kilogram block? I don't think so. So let's move on to the 3 kilogram block. I'll draw it in red. I just realized I'm drawing these diagrams in the Christmas colors. That was not on purpose, but I mean, it was bound to happen eventually. I don't have that wide of a selection of colors after all. Okay, 3 kilogram block. So it's going to have a force of gravity, I guess we'll call it force of gravity 2, since it's block 2, is equal to 3 kilograms times g. There's going to be, I'm going to call it normal force table. There's going to be normal force blocks pushing down on it because of the block above it. This thing is trying to move right, not only relative to the table, but it's also moving right relative to the 2 kilogram block if the system moves the way I expect it to. So opposite to the direction of its motion would be left. Force of friction kinetic between the blocks. Friction would drag the 3 kilogram object back to the left, or at least it would try. And of course, we can also use the Newton's third law reasoning here. These two frictions are action and reaction. And also we've got a rope to its left, so that's going to be force of tension 1. And a rope to its right, that's going to be force of tension 2. And I think we are done with block 2. Definitely the most complicated one so far. The 10 kilogram block, on the other hand, is the simplest. The 10 kilogram block is just going to have force of tension 2 pulling up on it. Let me wall this off, hold on. Yeah, there we go. So force of tension 2 upward and force of gravity 3 downward is equal to 10 kilograms times G. Okay. 3 objects, 3 diagrams, 3 sets of equations. Let's actually pick another color here. I'm starting to see too much green on the screen. Let's see. So, net force vertical on object 1. So, net force on object 1 in the y direction has to be 0. I don't expect the 2 kilogram block to accelerate up or down. Equals just normal force between the blocks minus force of gravity 1, which is 2g. So that tells me that normal force between the blocks is equal to 2g is equal to 19.6 newtons. We'll hold on to that. We need that in order to calculate the friction between the blocks. Speaking of, net force on block 1 in the x direction equals the mass of block 1, 2 times the acceleration of block 1 is just going to have magnitude of acceleration of the system. Positive direction for the 2 kilogram block is going to be left. 2 kilogram block, its positive direction is going to be left. So force of tension 1 is positive minus force of friction kinetic between the blocks. That's going to be negative. Equals force of tension 1 minus the coefficient of friction was 0.3 times the normal force was the normal force between the blocks, which is 19.6. I believe that's going to be 58.8. Or no, 5.88, right? 0.3 times 19.6. Yeah, 5.88. Okay, so force of tension 1 minus 5.88. We'll hold on to that and go back to it later. Object 2. We actually don't need to do net force y for it, but I'll set it up. Net force on object 2 in the y direction is going to have to be 0. And is going to be normal force table minus normal force blocks is pushing down on it, and also minus 3G pulling it downward. And we're not going to go any further with that. Net force on block 2 in the x direction equals the mass of block 2, 3 kilograms, times the acceleration of the system, is equal to, let's see, for 3 kilogram block, the positive direction is to the right. So right minus left, force of tension 2 minus force of tension 1, and also minus force friction kinetic between the blocks. Or tension 2 minus tension 1 minus the 5.88. I'll just leave it as 0.3 times 19.6 for now, just so that we can more easily spot that they're going to be the same number between these two. Okay, and we only have one net force equation for the 10 kilogram block because we don't have anything in the x direction. So net force on block 3 in the y direction is going to be positive direction for the 10 kilogram block is going to be down this time. So 10 times acceleration of the system equals down minus up 10g minus force of tension 2. All right, we can put this equation and this equation and this equation together. We can add them all to each other. So 2 acceleration of the system plus 3 acceleration of the system plus 10 acceleration of the system gives me 15 acceleration of the system equals, let's see, we have tension 1 minus friction plus tension 2 minus tension 1 minus friction. So tension 1 and minus tension 1 are gone. And then plus 10g minus tension 2. So the tension 2 from there minus the tension 2 from there would all be gone. So the 2 tensions are gone, and we're just left with the 10g and the minus 0.3 times 19.6 twice. So that was minus 2 times 5.88 is another way of writing that. Okay. Actually, you know what I could have done? I could have just kept this as 0.3 times 2g. And then this would have been, well, I guess it wouldn't have mattered, but I could have done minus 0.3 times 2g, which is minus 0.6g. And then I would have had 10g minus 0.6g equals 9.4g. But either way, we're still going to get the same result in the end. So 10g, which is 98, minus 2 times 5.88 is 86.24. So 15 acceleration of the system is 86.24 newtons. And divide both sides by 15, and what do we get? 5.7493333. 5.749. I'm going to round that to 5.75. Acceleration of the system is approximately 5.75. I don't really use the approximately equals symbol all that much. I don't know if that's a good thing or a bad thing. Okay, so I think that answers one of the questions. Well, actually two, because the questions were for part A, draw a free body diagram for each block, which we did. Part B, determine the acceleration of each block. We did, and it came out positive, which tells me that my guess for the direction was correct. If it did come out negative, I would have to go back and revise my diagrams because it would mean that the direction of my friction would also have been wrong based off of that assumption. Of course, we all knew just through common sense that wasn't going to be the case. There is no universe in which this system would be moving in the opposite direction. No universe where this 2 kilogram block would move to the right while pulling everything else up. Not without some sort of applied force anyway. So that's part B, and then part C is finding the tensions, which we know how to do. You plug in your acceleration into some of your older equations and solve for the tension forces. You plug in 2 times 5.75 over here, and you solve for force of tension 1, and then you can plug in over here as well, 10 times 5.75, subtract the 10g, and then I guess take the negative of that, and you've got force of tension 2. We know how to do that by now, so I'm not going to bother with that. This is actually a good practice, by the way. Once you get to the point in a problem where the rest is just easy stuff that you've done 100 times before and you know how to do it, use your time efficiently and just move on to another problem. Once you've got the core of setting up the problem and the rest is just calculations that you know how to do, consider yourself done. Unless, of course, it's on a test, in which case you have to fully answer the problem to get credit. But when just doing random practice on your own, you don't have to fully solve the problem. Just solve it far enough to where you've done the hard part that actually needed practicing. Okay. Actually, I think I did this problem in one of my older videos, come to think of it, but it doesn't hurt to have it in there. Although I do feel that I've done it before. Actually, I can check. I think I still have... Give me a minute here. I think I still have... Oh, no, it's not on that list. Let's see. Ah, I see. That problem on the next page was done in that video. Okay, then I'll probably avoid that one. But for everything else from this point onward, I think we're in the clear. Okay. I'm glad I double-checked that. Next up, we have, this one just requires a bit of geometry, but otherwise is not a very terrible problem. So it says, and I guess I should draw the diagram first before reading it. They've drawn a boat. They've drawn a boat in water. They've drawn a boat in water, and then this is a top view of the boat, so we're looking at it from like a helicopter above. I guess, where's my... Hold on. Gotta find an excuse to use this thing. The giant eyeball of physics. So, we're looking down on it like this. Giant eyeball looking straight down from above at the boat. That's our perspective. And we also see a sail. I'm probably not going to draw this very well, but we're looking like from the top at a boat's sail, and it's catching wind and it's exerting a force. By catching wind, it creates force on the boat that they've drawn on the diagram like this, and they've called it F sail. Then they've got another force they've drawn over here, which is the force of the keel. F keel. They've drawn like that, and they used the arrowheads in their diagram, so I'm just copying that over. And they also drew that line over there, which is along the north direction. Making that east. And they said that this angle over here is 30 degrees. That angle right there is 30 degrees. I should have drawn this bigger so that it would look nicer. Okay, and it says the force exerted by the wind on a sailboat is approximately perpendicular to the sail and proportional to the component of the wind velocity perpendicular to the sail. For the 800 kilogram sailboat shown in the figure, the proportionality constant is, and then they give us an equation. They say force of the sail is equal to 550, and then they have it in units of newtons per meter per second, times V wind perpendicular. Actually, the perpendicular symbol is a subscript of the word wind, so you have a subscript within a subscript. Huh. Good to know that that's allowed, but how deep can this go? I'm sure people are going to start memeing with layers and layers and layers of subscripts. Actually, I would imagine somebody has already done it, and all I need to do is just search for it. So I'll reread that part of the problem later. There's a second paragraph, so it says, water exerts a force along the keel, which is the bottom of the boat. So if we were looking at the boat sideways, the keel of the boat would be kind of like this fin-shaped thing that stays under the water. So here's the water, and then there's the boat and the sail, and the keel is this sort of fin-shaped thing. And its purpose is actually to catch water so that the water equivalent of air resistance can help keep the boat balanced. Those of you in Physics 1 will get to learn about this some more when we talk about fluid mechanics. But yeah, it says water exerts a force along the keel of the boat that prevents it from moving sideways, as shown in the figure. So that's to say that whatever this force is, it's just going to counter the horizontal component of F sail, meaning that our net force is just going to be along the north direction if we have one. So once the boat starts moving forward, water also exerts a drag force backwards on the boat, opposing the forward motion. If a 17-knot wind, where 1 knot is equal to 0.514 meters per second, is blowing to the east, what is the initial acceleration of the sailboat. Okay, so they're saying water exerts a drag force backwards on the boat. So there's going to be some force to the south, but we're not worrying about that. So basically, this is kind of like that air resistance problem where they're just talking about before the drag kicks in. So we don't need it on our diagram. They're just mentioning that it's going to kick in eventually, but they're asking us what is the initial acceleration of the sailboat. That's like asking what's the initial acceleration of an object dropped from rest. Its initial acceleration would be 9.8 before any air resistance builds up against it. Same idea here. What acceleration will it have before any water resistance builds up against it, is what they're asking. So they said V wind equals 17 knots. And they said one knot is equal to 0.514 meters per second. And also they said this was to the east. This was straight to the east. Okay, so like I said, most of this is really just geometry that you have to do. So I'm going to redraw the sail over here. I'm going to redraw the sail. I'm just going to draw a line representing it, rather. So oversimplified sail. So we have, that's going to be our sail. That's our 30-degree angle. And then it catches, there's wind coming at it. There's wind coming at it. And that wind velocity is 17 knots, which we can convert to meters per second in a minute. So that's V wind. And we need to calculate the force of the sail. We need to calculate F sail, which depends only on the part of the wind that's perpendicular to the sail. And that makes sense if you think about it. If this wind is blowing to the east, then you could say it's a combination of wind blowing this way, parallel to the sail, which is just going to glide past the sail and not do anything. And then the other part of it is perpendicular, directly blowing at the sail and pushing against it. So yeah, that makes sense to me, that we would only take the part of the wind that's perpendicular to the sail. So we're going to have to break this V wind into components. It looks like one of its components is going to look like that, and one of its components is going to look like that. And we need to figure out what these angles are in order to do that. So if this is 30 and that's 90, then that would have to be 60. And since this component is perpendicular to the sail, that would mean this 60 and this angle over here have to add up to 90, which means this has to be 30. And we're done. So this would have to be V wind cosine of 30 degrees, since it's touching the 30-degree angle, and that would be V wind sine of 30 degrees, but we don't need it. We only need this component, the perpendicular component. So that's V wind perpendicular equals V wind cosine 30. And then once we have that, plug it into here, and that'll give us F sail. And then we need to calculate, let's see. They didn't give us a formula for F keel, but they did say it's going to cancel out the, I guess, eastward component of F sail. So we need to figure out what the northward component of F sail is. More geometry. I know this is a 90-degree angle, which means that's a 90-degree angle. So if I draw another copy of my north direction there, let's see. If that's 60, then this would have to be 30, and this would have to be 30, which means this would have to be 60. So that would mean F sail, so I'm going to draw F sail with a component like this and another component like that. We don't need to worry about that component, it's just going to be canceled out by F keel, whatever it is. We just need to worry about this north-facing component, which is touching the 60-degree angle. So it's going to be F sail cosine of 60 equals F sail north. So F sail north equals F sail cosine of 60 degrees. Or you could also say that it's sine of 30 degrees. Cosine of 60 is equal to sine of 30. We might see something interesting as far as the trigonometry is concerned if we switch to sine of 30. We'll see in a minute. Let's put together what we know. So net force, I guess we'll say net force north is going to be just, well, the mass of the boat. Was the mass of the boat mentioned? Yes, it was. It was 800 kilograms. Actually, let me reread. So it said the force exerted by the wind on a sailboat is approximately perpendicular to the sail and proportional to the component of the wind velocity perpendicular to the sail. Yeah, that is basically what we just finished elaborating on. For the 800 kilogram sailboat shown in the figure, the proportionality constant is, and then they give you that formula. Okay, yeah, we're all caught up. So 800 kilograms times the acceleration. Initially there's no drag, remember. So 800 times, I guess we'll call it, we don't need to call it anything special. It's going to be the initial acceleration, equals just force sail north. F sail north, which equals F sail times cosine of 60. F sail times cosine of 60, which equals F sail is going to be 550 times V wind perpendicular, which is V wind times cosine of 30, cosine 60. Well, if I rewrite the cosine of 60 as sine of 30, then I guess the only real thing that would happen as far as the trig is concerned is I could simplify it to 1/2 sine of 2 times 30, 1/2 sine of 60, which doesn't really do anything special for us here, but might have some uses in other places. Maybe if we had more of these boat problems, I could find a pattern where it would be useful, but I'm not seeing anything else that would make it worth it to go through all that trig. I mean, it's only one step, but still. So V wind, let's go ahead and convert that to meters per second. So 17 knots. I guess we'll do it up here. 17 knots times every 1 knot is equal to 0.514 meters per second. Knots cancel out and we're left with meters per second. So 17 times 0.514 is 8.738. 8.738 meters per second. Okay, so 550 times 8.738 times cosine of 30 times cosine of 60 equals 800 times the initial acceleration of the boat. So let's do 550 times 8.738 times cosine 30 times cosine 60. And I'm getting 2081.015744. Divide that by 800, and I get 2.60126. I'll just round to 2.60. Acceleration is about 2.60 meters per second squared. All right, and there's the end of that one. So the real challenge with that was, again, like I said at the beginning, is just doing the geometry, which wasn't particularly hard, but you just have to slow down. And the other big challenge was the reading comprehension. If you thought language did not matter, this is one of those problems that illustrates the importance of slowing down and reading and understanding the problem. If you don't interpret the problem correctly, what hope do you have of actually solving it? But I think we're ready to move on to another problem. We've got an hour left. Let's see how many we can squeeze in. Probably 3 or 4. I noticed, despite feeling like I was going pretty slow last time, I think I was averaging like 15 minutes per problem, which is not too bad. I thought I was going slower than that. I mean, either way, I have to go slower because I'm pausing to explain things. I know I've talked about that before, but it bears repeating. Let's see, what is the resultant force exerted by the two cables? That's just a symmetric situation. We've done something like that before. Well, I don't think we've done symmetric before, but we've done a problem where you have two ropes at angles holding something up. Yeah, we don't need to do that one. What about this one? Baseball pitcher throws a ball straight up into the air at a speed of 20 meters per second. Not really, just a very classic kinematics into force problem. We don't need that. And that one is force into kinematics. We don't need that. Minimum force of friction required to hold the system in equilibrium. It's just a block on a table and another block hanging vertically. We've done stuff like that before. And we've done a box on top of a truck before, so no need for that one. Oh, okay. This one isn't too hard, but it is a little bit different from what we're used to, so it might be worth looking at. So they have a block that's being pushed against a ceiling, and it's being pushed at an angle. So you've got a block being pushed against the ceiling at an angle. What color do I want here? Let's use red. Actually, no, let's use this one. Whatever you want to call it, burgundy. So they've drawn a 55-degree angle over here. They said this was 55 degrees. And the force, according to the drawing, is 85 newtons. 85 newtons of force. And they've got a block. It's 4 kilograms, so mass equals 4 kilograms. It says a 4-kilogram block is pushed along the ceiling with a constant applied force of 85 newtons that acts at an angle of 55 degrees with the horizontal. As in the figure, the block accelerates to the right at 6 meters per second squared. Acceleration, 6 meters per second squared. Determine the coefficient of kinetic friction between block and ceiling. That is the question. What is mu k? Pretty simple problem. It's just that usually we look at the upside down version of this, so might be nice to just try and look at something where the surface is the ceiling instead of the floor for once. So we can break this force into 2 components, a component to the right and a component upward. And actually we need to finish drawing the diagram of this thing, so let's do it over here. So here's our block. We've got the 85 Newton applied force. So there's force applied. And then there's going to be a normal force between the surface and the block. The surface this time is above the block, so the surface is going to push down on the block. So that's going to be the normal force. And there's mention of friction. If this thing accelerates to the right, then assuming the ceiling isn't also accelerating, should be easy to conclude that the force of friction kinetic must be to the left. And there we go. And of course that drawing is not to scale. Okay. Nothing too bad from here on out. So net force, I guess we'll do net force vertical first because we need to determine the normal force. Net force vertical. Actually, we need to do horizontal first because this time we actually have enough information for the horizontal. So net force vertical has to be 0. Equals forces up minus down. So forces upward would be the 85 times sine of 55 degrees. So 85 sine of 55 degrees minus the normal force. And that tells us normal force is 85 sine 55. Net force in the x direction is not 0. It's going to be the mass, which was 4 kilograms, times the acceleration, which was 6 meters per second squared to the right, equals forces to the right minus the left. Forces to the right would be the rightward component of the applied force, so 85 cosine of 55 degrees, minus the force of friction, which is going to be the coefficient of kinetic friction, which we don't know yet, times the normal force, which we can get from here is equal to 85 sine of 55 degrees. Okay, subtract 85 cosine 55 from 4 times 6. So 4 times 6 is 24, of course, minus 85 cosine of 55 is negative 24.754, give or take. And that's equal to negative mu k times 85 sine 55. So divide by, well, we get rid of the negative, so divide by the negative sign and divide by negative 85 sine 55. That gives me positive 0.238. I get mu k equals 0.23, well, 0.2385, so I guess it would round to 0.239. Okay, that wasn't too horrible. I mean, I wasn't expecting it to be. Just a little bit different. Could potentially throw people off, so it was worth it to look at. What about this one? Frictionless plane is 10 meters long and inclined at 35 degrees. A sled starts at the bottom with an initial speed of 5 meters per second up the incline. When the sled reaches the point at which it momentarily stops, a second sled is released from the top of the incline with an initial speed of v initial. Both sleds reach the bottom of the incline. Ooh! Oh, this one might actually be a good one. Oh yeah, I'm liking the sound of this one. I've got this big unused gap over here, but it's not going to be enough for this problem. Poor planning on my part. I don't like wasting paper, but I'm sure many of you have noticed that a long time ago. You have probably been annoyed by my habit of trying to get as much mileage as possible out of my paper. I don't like being wasteful. I've seen way too many just, I don't know, things like half-eaten food being thrown out and people breaking things needlessly just to, I don't even know if they're trying to show off that they're tough or whatever. People mishandling things, like the way they kind of forcefully swing open their laptops and Chromebooks. Oh my goodness. Contrast that with, there was a video I saw a while ago about, they went to like, I think it was from the Abroad in Japan channel on YouTube. Abroad in Japan. I think they did an episode where he went to one of those like used goods stores. I forget what it was called. And just showed you all these used items that you would expect to be, you know, really old and rusty, and they're in pristine condition because people in Japan, I guess it's part of their culture, they take really good care of their things. If only more people were like that. Anyway, let's get to the problem. So a frictionless plane Oh, it would have been so much more interesting if we added friction to it, but again, that's an opportunity for you. Add friction to this problem and see how that changes things. But they have a frictionless plane. It's 10 meters long, and when they say 10 meters long, they mean this way. So a frictionless plane is 10 meters long and inclined at 35 degrees. A sled starts at the bottom with an initial speed of 5 meters per second up the incline. So sled starts, so I guess we'll call it sled 1. Starts at 5 meters per second up the incline. When the sled reaches the point at which it momentarily stops, so it's going to go up, slow down, slow down, slow down, it's going to reach some point, it's not going to reach all the way to the top, it's going to reach some point, pause for a second, and then slide back down. Not even a second, pause for a split second, a very, very tiny infinitesimal fraction of a second, and then slide back down. At that moment, a second sled is released from the top of the incline with initial speed unknown. So a second sled is released. I guess we'll extend the incline by a little bit. A second sled, sled 2, is released with V initial. It's given some sort of push down the incline. Both sleds reach the bottom of the incline at the same moment. Determine, for part A, the distance that the first sled traveled up the incline, and then for part B, determine the initial speed of the second sled. Okay, so first part is pretty easy. You just figure out what the acceleration is and do some kinematics. It's not really that bad. So first part, we would just draw a diagram of this thing. Actually, both of these would have the same diagram when they're in motion. So you would have force of gravity straight down, which is going to have two components. Force of gravity sine of theta, which I guess they didn't really tell us now, did they? Oh, wait, yes they did. They told us it was 35 degrees. I must have blanked on that part. So force of gravity sine of 35 degrees. That way, and then force of gravity cosine of 35 degrees that way. And of course it's going to have a normal force, which will cancel out that cosine component, and no friction, so that's it. And it's going to be the same for both blocks. Both blocks are going to have the same diagram, so we nailed two birds with one stone today. So net force perpendicular, nothing exciting there. Net force parallel to the incline is going to be equal to the mass of the block times the acceleration is equal to mg sine of 35 degrees. It doesn't matter what the mass of the block is. Both blocks are going to have an acceleration of g sine 35 down the incline. So I guess we're going to have to determine what we want our positive direction to be. I want down the incline to be positive for this problem. I think that'll make things simpler, which I guess means we have to start with negative 5 meters per second for initial velocity of block 1. Yeah, that's what I'll do. So down the incline is positive, which means this acceleration ought to be positive as well, which is exactly how I have it. No need to flip signs. So acceleration is equal to g sine 35, 9.8 sine of 35 degrees is 5.62. We're getting about I'll round it to 5.6 meters per second squared. Okay. And that's part A. Determine the acceleration. No, part A is determine the distance at which the distance that the first sled travels up the incline before it comes to a stop. It's gonna be, let's see, in 1 second, it looks like it's gonna be only 2.5 meters. If my math is right, close to it anyway, because with an acceleration of 5.6, this thing is going to be going up the incline for less than 1 second. Right, the 5.6 is going to eat through the 5 in less than 1 second if it goes through 5.6 per second. So yeah, less than a second. And in less than 1 second, if you start off with 5, if you had a full second starting off with 5, then your average between there and when you come to a stop, the average between 5 and 0 would be 2.5. So 2.5 times 1 second. Yeah, I'm expecting something like 2.3, 2.4-ish, probably. Let's actually do the math. So it would be third equation. V final squared equals V initial squared plus 2 acceleration times, I guess I'll call it delta S. And then that's going to be 0 equals negative 5 squared plus 2 times 5.6 times delta S. Subtract 25 on both sides and divide by 2 times 5.6. So negative 25 divided by, well, I'll divide by 2 and then divide by 5.6. Be careful about that. I know I've warned about that before, but if you type, I'll put my calculator up here. If you type negative 25, whoops, what did I do? If you type negative 25 divided by 2 times 5.6 like this, you're not going to get the right result. Use parentheses if you're going to do that, or just make sure you understand your order of operations. Negative 2.23214 is what we should be getting. The negative sign just means the displacement is in the negative direction. We already said down the incline is positive, so that's not really a surprise to me. Negative 2.23. So delta S is negative 2.23 meters, and distance, I guess we'll say, is the absolute value of that is 2.23 meters. Okay, that's our answer for part A. Part B, determine the initial speed of the second sled. They both have to arrive at the bottom at the same time from the moment that the first sled has already risen to this point. So sled 1 is essentially starting from rest. So now sled 1 is up here. starting from rest, and it has to go down 2.23 meters. And it has to go down in the same amount of time that sled 2 goes down 10 meters. And we need to solve for V initial of sled 2 that would make that happen. So we need to figure out how much time sled 2 has to move, and we can figure that out using the time that sled 1 takes. Actually, I think it should be the same amount of time that it took sled 1 to get up to here from the bottom in the first place, if my intuition is right. But anyway, we can just do second equation. So second equation tells us delta S. This time it's a different delta S from what we had before. I guess I'll call this delta S rise. Delta S rise of object 1. And then delta S fall of object 1 is going to equal V1 initial times T plus 1/2 A T squared, V initial being 0, delta S fall being positive 2.23, since now we actually are moving from up here to down here, positive 2.23 meters, equals 1/2, what was the acceleration again, 5.6, times T squared, multiply by 2, divide by 5.6. We should get something less than 1. 2.23 times 2 divided by 5.6, and then take the square root of that, and I get 0.892 seconds. T equals 0.892 seconds. And we need to use that to figure out what initial velocity object 2 must have. We can just use second equation of kinematics again. Delta S fall of object 2 this time is going to be equal to V2 initial, or just V initial as they called it, times T plus 1/2 A T squared. So 10 equals V initial times 0.892 plus 1/2 5.6 times 0.892 squared. What is my prediction going to be for V initial? If you've got less than 1 second to go down 10 meters, in less than 1 second, you're going to be gaining less than 5.6 meters per second squared. So we'll say you gain about 5. If you gain about 5 and you have less than a second, you want to average a little more than 10 meters per second. So if you're gaining 5, then you want to start out maybe at around 7.5, a little bit more than that. Just doing a little bit of mental math there. So 10 minus all that, 10 minus 2.8 times 0.892 squared is 7.772, and then divide that by 0.892, and I'm getting 8.713. I'll just round that to 8.71. So V initial is about 8.71 meters per second, which fits my prediction. A little more than 7.5 meters per second. Okay, not bad. And let's, of course, circle that. So, one thing you could add to this, one little twist, is you could ask yourself, how does this problem change if friction is introduced? Give yourself a coefficient of friction of whatever, 0.1, 0.2. Don't go too high, because then you're going to get some sort of unreasonable result. And we definitely don't want that. You don't want to go too high, otherwise sled 1 just won't come back down. But yeah, if you introduced a coefficient of kinetic friction, how would the problem change under those circumstances? That's another bonus question you can ask yourself. Another question you could ask yourself is, with what initial velocity must this block be released if it is to meet sled 1 at the moment where it gets to this turning point? That's another question you could ask. See, there's a lot you can do. There's a lot you can do to add twists and turns to a problem. So if you're working with a textbook that doesn't have the best of problems, you can make your own based off of them. This one, just 3 objects connected by ropes on a pulley. That's nothing too strange. This is a friction problem that requires you to look up coefficients of friction from a table in the book, which I don't know if I ever talked about that when discussing friction, but the textbook that we're using, I think I may have mentioned it. I feel like I did, but it doesn't hurt to go over that real quick. So let me switch over to the book. We do have, let me see, over here. Yeah, here we go. So there is a table of friction coefficients in this book. If you were looking at problems in the book, some of them may have expected you to use this data table to look up information. So if you felt that a problem was given to you without supplying enough information, then chances are they meant for you to look at this. In case I didn't go over that before, better late than never. But yeah, I've got a problem here that's got 2 different materials, well, 3 actually. We've got, let me read through it and see if it's a good problem. A 2 kilogram aluminum block and a 6 kilogram copper block are connected by a light string over a frictionless pulley. The 2 blocks are allowed to move on a fixed steel block wedge of angle 30 degrees as shown in the figure, and we can draw it if I decide we need to do this problem. Making use of the data table in the chapter, determine the acceleration of the 2 blocks and the tension in the string. Yeah, I don't really think we need it. But if you want to see what the diagram looks like, I can draw it for you over here. They've got a pulley and then one block over here, another block over here. This one is aluminum, this one is copper. and this surface itself is made of steel, so you would look for coefficients of friction of aluminum versus steel and copper versus steel. And they gave you an angle over here of 30 degrees for the incline. The aluminum block is just going to be on a completely horizontal side of this thing. And they said the aluminum block is 2 kilograms while the copper block is 6 kilograms. And yeah, that's it. And it says the blocks are allowed to move. It doesn't tell me if they were released from rest, so you need to take that into consideration. Calculate based off of static friction first, and see if the static friction is high enough to prevent motion. If it is, then... Oh, actually, I think I'm remembering something about this problem. What was it? I think it was going to end up being the case that static friction is high enough to prevent the system from moving, but the interesting question is which block, if either, has its static friction maxed out. Yeah, I think that was the question for that one. I think I'd actually like to save this one for like a traditional office hours session. I'm going to need to make a note of that. I'm going to need to remember that. I think that's a good problem for traditional office hours, along with a couple of other physics problems that I need to get around to. Speaking of traditional office hours, I'm not going to do it same day, but I have to do something. I don't want to make promises, but I really, really want to get one out this week because it's been too long. But I still have all these other things to get caught up on. Some of it may not be as serious, but it is winter break, and I am kind of falling behind on my gaming schedule. And I need to get caught up there as well. So, yeah, the ironic thing is I started game streaming because I wasn't touching my video games that much, and I wanted to use that as a way to force myself to go through my backlog, which continues to grow. By the way, Steam Winter Sale, in case you weren't aware, is happening right now, so all you PC gamers, you might want to look at some of those nice discounts. But anyway, let's get back to physics. So that problem I already did in a previous video. That was simple enough, we don't need it. Don't need that. Yeah, that one is simple enough, so not going to bother with it. This one I guess we haven't seen before, we might as well take a look at it. Actually, do we have... between this one or that other one? Maybe we can do both. So this one says we've got a 3 kilogram object that hangs at one end of a rope that is attached to a support on a railroad car. And they've drawn it like this. So it's inside of a moving vehicle, and they've given us X-ray vision, and here's what we're seeing. I've drawn the angle rather exaggerated, but it's supposed to be 4 degrees. So this thing is inside of a vehicle that has some sort of acceleration to the right. It's a 3 kilogram object. M equals 3 kilograms. And yeah, when the car accelerates to the right, the rope makes an angle of 4 degrees with the vertical as shown. Find the acceleration of the car. That is the question. Find the acceleration of the car. That's all. So somebody standing inside of this train, from their perspective, they see this thing pretty much sitting still. Of course, it's not going to be perfect. It's actually going to wobble because we live in an imperfect world. But in a perfect world, this thing would just be sitting completely still, as if it's magically levitating in place. So what's going on there? What's going on is, of course, if the train is accelerating to the right at whatever number of meters per second squared, then this thing is gonna have to keep up with the train. Everything in the train needs to accelerate at the same rate in order to not separate from the train car. So in order for that to happen, there needs to be a force to the right, and that's not going to be the case if the object was just hanging, straight vertically. There wouldn't be a horizontal force on it. So that's really all there is to it. There's going to be some force of tension on this thing. There's going to be some force of tension, and of course there's going to be a force of gravity. And this force of tension serves two functions. One, it keeps the object from falling straight down. There's enough tension upward to counter the force of gravity, but also it's going to have a horizontal component that allows it to keep pace with the train car. So let's go ahead and figure out what that tension force must be. What was the question actually? Find the acceleration. But yeah, for that we need to find the tension anyway. So force of tension, two components. It's going to have one component there and one component there. The upward component, well, if I were to redraw, so here's the upward component, then there's the string itself, and then that is supposed to be my 4-degree angle. That would mean that this over here is 4 degrees. So the upward component is adjacent to the 4-degree angle. It's going to be force of tension times cosine of 4 degrees. So net force Y needs to be 0 equals forces up, that's force of tension cosine of 4 degrees, minus forces down, that's just going to be mg, 3 times 9.8. Net force horizontal is, well, all we have is the force of tension to the right. So that's going to be the mass, 3 kilograms, times the acceleration, we don't know yet, equals force of tension sine of 4 degrees. We can solve that first equation for the tension force since tension is the only unknown here. Add 3 times 9.8 to both sides. What is that? 29.4. 29.4 equals force of tension cosine 4. Divide both sides by cosine 4. So 29.4 divided by cosine of 4 degrees is 29.47. I don't think I mentioned this today, but as always, remember to check the mode of your calculator and make sure that you are in the correct mode. We are working in degree mode. There's going to be just one situation in AP Physics 1 and C where we're going to use a radian mode, and we'll talk about that when we get to it. It's not even a whole chapter, it's just a specific part of a chapter, a specific set of formulas within that chapter. But anyway, 29.472, I'm going to say. Force of tension. Using that equation gives me 29.472 newtons. Okay, and then plug that in here and divide by 3 and we get the acceleration. Nothing too bad, might as well do it real quick. So force of tension 29.472, whoops, 472 times sine of 4 degrees, and then that result divided by 3 gives me 0.685. I'm getting acceleration equals 0.685. I'm not too surprised by that. Trains don't really move that fast. They take a while to build up speed at the very least, and that's also why they don't stop very quickly. They don't speed up very quickly, and they also don't slow down very quickly, so don't play on train tracks. Okay, next problem is just a pulley problem with 3 blocks instead of 2. Nothing super fascinating there. We already did something like that. Although that one was harder than this one. Let me give this one a read. I think this one is more of a thinking problem. It says, an inquisitive physics student wishing to combine pleasure with scientific inquiry rides on a roller coaster sitting on a bathroom scale. Do not try this yourself on a roller coaster that forbids loose, heavy packages, which ought to be all of them. So yeah, warning, don't bring a bathroom scale into a roller coaster. If it falls, it's going to hit someone in the head, and that's a lawsuit waiting to happen. Don't do it. The bottom of the seat in the roller coaster car is in a plane parallel to the track. The seat has a perpendicular back and a seat belt that fits around the student's chest in a plane parallel to the bottom of the seat. Wait, really? That fits around the students. Oh, okay. I was misinterpreting that because I was thinking like, wouldn't it have to be perpendicular to the seat? But okay, now I'm understanding it. The seat belt is the way it wraps around you is parallel to the seat, but the force it exerts on you actually is also parallel to the seat. Okay, I see. So its purpose is increasing friction. Anyway, the student lifts his feet from the floor so that the scale reads his weight, 200 pounds, when the car is horizontal. Okay, so they're sitting on it, I guess. Right? Did I read that correctly? Yeah, rides on a roller coaster sitting on a bathroom scale. That was the first sentence. Okay, you have to read and reread these questions multiple times to make sure you understand the situation. Anyway, his weight, which is 200 pounds, is read when the car is horizontal. At one point during the ride, the car zooms with negligible friction down a straight slope inclined at 30 degrees below the horizontal. What does the scale read at that point? Oh, okay, this is actually a math problem, but It's actually pretty easy math if you remember what we said about bathroom scales. A bathroom scale, I'll grab mine real quick. A bathroom scale does not actually measure your weight. It measures whatever force is exerted against it. And by Newton's third law, that's also a measure of what force it exerts against you. So if you are sitting on the bathroom scale while in a roller coaster that's going down an incline, what it's actually measuring is the force that it exerts on you perpendicular to that incline, which would be the normal force. That's the normal force. Same thing, actually. Forget about inclines. What about all those elevator problems we did where we talked about, what's the normal force when the elevator is accelerating up versus accelerating down versus whatever? If you brought a bathroom scale into an elevator and you stood on it, you would see when the elevator accelerates up, the reading on the scale goes up with it because it's not reading your weight, it's reading the normal force. When you need to accelerate upward in an elevator, the upward force on you, which is mainly going to be the normal force, has to be greater than your weight. And the reverse is true if the elevator accelerates down. Although usually with the way elevators work in real life, you're only going to see it for a split second doing that because the elevator will probably just coast at a constant speed after it builds up whatever velocity it needs. You'll see it just quickly go up or down depending on which way you're taking the elevator, and then the reverse will happen when it slows down just before it's about to arrive at the floor that you are sending it to. So yeah, there's that. I'll just put it over here and deal with it later. So yeah, it's just going to read the normal force. Just draw a diagram of an object on an incline like that, and it's just going to read their weight times the cosine of the angle, and you're done. I don't think we need to spend any more time on that one. Speaking of time, I don't think we have time for more than just one additional problem, so let's see if I can pick something that I can make count. Okay, here's one that we can probably wrap up with. Oh wait, already used that color. Let's try something different. What have I not used in a bit? I got you. I guess we haven't used a lot of pink. And I guess this navy blue, which is probably not going to look all that different on the camera, but that's probably more of a lighting issue or just something I have to toggle in the camera settings some more. Okay. So it says a van accelerates down a hill. So they've actually drawn it in a diagram, which is nice. So it says a van accelerates down a hill, and they show this figure. They've got some angle theta over here, and then they've got the van. And then they have a drawing inside the van of an object hanging off of a string, and then they've got that vertical dotted line, and then this angle over here is also equal to theta, is equal to the same angle as the incline. So that's theta. That's not even readable, is it? Well, I tried. That angle is theta. So it says a van accelerates down a hill going from rest to 30 meters per second in 6 seconds. Going from rest, v initial equals 0, to 30 meters per second in 6 seconds. During the acceleration, a toy of mass 0.1 kilograms, so that toy over there has a mass of 0.1 kilograms, hangs by a string from the van's ceiling. The acceleration is such that the string remains perpendicular to the ceiling. Determine the angle theta and the tension in the string. So those are the questions. What is theta? And what is the force of tension in the string? Those are the questions. Well, we know that, similar to the train problem that we just did, actually, we know that the acceleration, whatever acceleration this thing has, and this doesn't actually depend on what the angle is, as long as this thing could have been hanging at an angle greater than theta or less than theta. As long as it was hanging still at whatever angle it was hanging at, we would know that its acceleration has to match the acceleration of the vehicle. Otherwise, you're going to see either the vehicle moves forward faster than it and it continues to swing backwards as a result, or the vehicle accelerates slower than it does, in which case it would swing in the opposite direction. And that's actually what happens in the beginning until the angle is just right for the object to end up with the same acceleration as the vehicle. So this is eventually going to happen, the object appearing to be still from the perspective of people in the vehicle. That's going to happen eventually. It's a matter of when, not if. Well, unless, of course, the string that it's hanging by isn't strong enough to supply the necessary tension. If the tension builds up in the string and builds up high enough that the string snaps, then that's another story. So, really the only thing unique about this problem is that we have this sort of special case for the angle. There is no reason why this thing has to go at an angle of theta to the vertical. But it just so happened to be the case here, which might simplify our geometry a little bit. Let me go ahead and think about what acceleration this thing needs to have. So I guess we're going to want to draw a force diagram on the van to figure out what the acceleration needs to be for this thing. So force diagram for the van would be kind of similar to this, actually. Did they mention any friction? Nope, so we're going to assume frictionless. So it's just going to be... Uh-oh. Is this pen dying? It can't be, right? It's still pretty full. It's going to be force of gravity, sine theta, force of gravity cosine theta, normal force, and that's it. For the ball, it's going to have a force of gravity straight down that also can break into the same components. So for the ball, it's going to have force of gravity sine theta and force of gravity cosine theta. And for the ball, just the tension force this time would essentially serve the same function as the normal force on the van itself. Yeah, actually, maybe the hardest part of this problem is just being initially paralyzed, not knowing what to do with it. It's marked in red in my book, which I don't know how often you see this in your textbooks, but some textbooks like to color code their problems based on difficulty, and red, or I guess pink, is closer to what this actual color is, indicates that it's like really hard, at least in the opinion of the authors. I've seen these red problems turn out to be trivial from time to time, so I guess the authors may have overestimated the difficulties of their problems. Anyway, so I can use this first diagram to figure out what the acceleration needs to be, and the acceleration is just going to be g sine theta from the math we did before, right? The mass of the vehicle times the acceleration is going to equal mg sine theta, and then the mass of the vehicle cancels out. So yeah, acceleration is going to be g sine theta. And then we can just use these three pieces of information over here along with... We can use these three pieces of information to figure out the acceleration, and then divide by g to solve for theta. So yeah, let's go ahead and do that. So from 0 to 30 in 6 seconds. First equation of kinematics, I'll do it over here since we have some space. V final equals 30 equals V initial, which is 0, plus acceleration times time. Divide by 6, the acceleration is 5. So acceleration equals 5 meters per second squared. 5 equals g sine theta. 5 over 9.8 equals sine of theta. Take the inverse sine of 5 over 9.8. And I'm getting 30.67 degrees. I'll round that to 30.7. I like to keep just one decimal place on my angles most of the time. So theta is equal to about 30.7 degrees. As for sine theta, I'm just going to keep it as 5 over 9.8 because that's a little bit more precise. But there we go, we solved the first part. And then what's the tension force over here? So for this, we actually need to know theta, or at least we need to know sine and cosine of theta. So let's see. Actually, keeping it as 5 over 9.8 isn't going to work. Yeah, we'll just plug in 30.7. So mg cosine theta is going to equal the tension force because the net force perpendicular to the incline needs to be 0 here. Force of tension needs to be equal to 0.1 times g times cosine of 30.7. So 0.1 times 9.8 times cosine of 30.7 degrees is about 0.843. I'm just going to round it to 0.84 equals about 0.84 newtons. So yeah, the hard part of this was actually just the thinking part and figuring out what it is you need to do. But if you just start off by drawing your diagrams, you'll be good. It might be a little unusual because you don't think of an object inside of another object as requiring two diagrams all the time, but that's kind of what we started with. We started with objects inside of elevators. So yeah, this is just, I guess we've come full circle back to problems with objects within objects. So yeah, it's really just a simple matter of you have two objects, you need two diagrams. Even if this angle were different, that would just mean you would need to figure out, according to whatever this angle is, figure out, how to get your perpendicular and parallel components of your tension force. The angle having to be theta over here actually made the problem easier for us, not harder. And I think that is where we will stop for today. Is there anything I can leave you guys with? Anything at all? I mean, I could look through some of these problems, I guess, and see if there's something I can pick out for you guys to try on your own. Okay, I guess I will leave you guys with this one, and we will start with it next time. So, new sheet. It says, a sled weighing 60 newtons is pulled horizontally across snow so that the coefficient of kinetic friction between sled and snow is 0.1. So they've got a drawing here of a sled. How did they? Okay, so they did something like that. And then they have a penguin over here. I'm just going to draw a block to represent it. But yeah, they have a sled weighing 60 newtons. So force, gravity, sled equals 60 newtons. And you can reverse engineer that to figure out its mass. And then they said coefficient of friction between sled and snow is 0.1, so that's going to be snow. And I guess that would be coefficient of kinetic friction is equal mu k snow. Hold on, let me rewrite that. Mu kinetic snow equals 0.1. And then they say a penguin weighing 70 newtons. So force of gravity, penguin, I'll just say peng for short. Actually, okay, we'll write out the full word. Force of gravity, penguin, is 70 newtons. And it rides on the sled as in the figure if the coefficient of static friction between penguin and sled is 0.7. So mu static for the sled under the penguin's feet. Of course, maximum is 0.7. Find the maximum horizontal force that can be exerted on the sled before the penguin begins to slide off. So if there's some sort of applied force over here, question is, force applied maximum equals what before penguin begins to slip, before penguin begins to slip. That is the question. So there's some sort of applied force here that is applied directly to the sled. The penguin on the sled gets dragged because of static friction. We've seen this before with that one truck problem that we did. And we kind of saw something similar to it today with the two blocks that were being pushed where one was being dragged by the other due to friction. Similar idea here. So the penguin stays firm on the sled up until a certain point. If you apply too much force, there's a point where the sled moves under the penguin's feet faster than the sled can drag the penguin along with it. What is that point? By now, I would assume sorry. By now, I would assume that you shouldn't have trouble doing this to the point where I might not even have to actually do this at the start next time, but I probably will because that's just kind of tradition at this point. So yeah, there's your problem, and then there's also the other block problem. Where did I put it? Yeah, there's also this other block problem if you want to rewind back to when I went over the details of that one. That might be something for you to try. And of course, keep looking in your own textbook, and if you don't have one, the OpenStax textbook, or just look around online and see if other people have interesting problems that they've posted from their teachers that might be worth practicing. And yeah, if you have anything in particular you'd like to see, mention it in a comment before next time. Speaking of next time, I will see if I can get caught up on my other stuff this week, and if I can, then there might be an extra stream, but otherwise the plan is to just do Sunday again. So I'll put it on the schedule for Sunday, but keep an eye out because I might move the next stream a little bit earlier in the week. And with that, I think we are done. Keep studying. Well, enjoy your winter break, but don't enjoy it too much. Practice if you need the practice, and keep at it. And we're getting close to, I guess, not the halfway point of the course quite yet, because this year they've added fluid mechanics. What would normally be the halfway point? So it's like the 44-ish % point of the course. So we're getting there. We're getting there. And it looks like getting done by February is probably not going to happen after all. We're probably looking at March, which is fine. That would still be ahead of the AP exam. But then again, maybe if I squeeze in some extra streams over the winter break, we can get back to a pace where we'll probably finish on February. So we'll see how it goes, but I'm just going to keep at it either way. Take care. Class dismissed. I'll see you in the next one.